In this video, we're going to do some review of trig and inverse trig functions. Let's start by drawing our two special triangles. The first one will be a 30, 60, 90 degree triangle. So there's our right angle. This angle here is 60 degrees and 30 degrees. And the side lengths of this triangle are 1, √3, and 2. In drawing this triangle, it's important to remember that the shortest side, the side of length 1, will be across or opposite the smallest angle. So we want to make sure that we've got our sides labeled correctly there. Our other special triangle, so right triangle, we got two sides of length 1. The hypotenuse has length √2, and our two angles here, both 45 degrees. So these are two triangles that we should be very familiar with. Now in calculus, we'll use radians more often than degrees. So let's do a little recap here of radians. Radians measures the length of the arc around a unit circle. Let's draw a diagram here. Unit circle, that's just a fancy way of saying a circle of radius 1. So let's get a rough diagram going here. Okay, roughly circle there, radius 1. And if we want to talk about an angle, we can talk about it in degrees, say 360 degrees. Or we can talk about that angle in radians. So let's imagine starting here and then rotating through an angle of 360 degrees. So that would be a full rotation. And we can look at what the length of the arc is that we traveled around. Well, we traveled around a full circle in that case. So we're getting the full circumference of the circle. We know that circumference of a circle is 2 pi times the radius. And in this case, our radius is 1. So the circumference of our circle would be 2 pi. And we're talking about a number of radians there. So 360 degrees is the same thing as 2 pi radians. More commonly, we'll actually think about 180 degrees. So if we started again here and we went through 180 degrees, we're actually just going through a half rotation in that case, so going halfway around that unit circle there. The length of this arc that we traveled around would just be pi radians. Okay, so often this is the fact here that we keep in mind. So if we wanted to take something like 30 degrees and turn it into radians, the secret here is just to multiply by pi radians and divide by 180 degrees, because pi radians is the same thing as 180 degrees. So we really just multiplied by 1. Okay, and then we can simplify this a bit. We can cancel out factors of 30 from our numerator and our denominator, and the degrees get canceled out as well. So we'd have pi over 6 radians. 30 degrees, same as pi over 6 radians. If we wanted to take, say, pi over 4 radians and turn that into degrees, well, we'll take our pi over 4 radians, we're going to multiply by 180 degrees and divide by pi radians, because 180 degrees is the same thing as pi radians, so we've really just multiplied by 1 here. We'll be able to cancel out the pi's. The radians will cancel out, and we'll be left with 180 divided by 4, so 45, and we'll be left with degrees. So pi over 4 radians, 45 degrees. Now, we will use radians so much in this course that it's really better just to think of our special triangles that we drew earlier in radians. So we got our 1, √3, 2 triangle. We've got our 1, 1, √2 triangle. And let's make sure that we can express all the angles here in radians. So this angle here is going to be pi over 3, same thing as 60 degrees. Pi over 6, same thing as 30 degrees. And over here, our two angles are pi over 4, same thing as 45 degrees. So let's focus on these two special triangles whenever we need to find values of our trig functions. Well, let's get into a little calculation now of how we actually calculate the values of the trig functions. We need to remember Sohcahtoa anytime we want to do something like calculate, say, sine pi over 6. So if we want sine pi over 6, let's remember sine is equal to the opposite over the hypotenuse. And we just go back to our special triangle here, work with respect to the angle pi over 6. Okay, so the opposite side has length 1, hypotenuse has length 2. All right, so maybe I'll actually add the intermediate step here to show what we're doing. Did opposite over hypotenuse was 1 over 2. So sine of pi over 6, 1/2. If we wanted cos of pi over 6, again, going back to Sohcahtoa, cos is the adjacent over the hypotenuse. And still working with respect to the angle pi over 6, the adjacent side is root 3, the hypotenuse is 2. So cos of pi over 6, root 3 over 2. Let's try one more. Let's say we want tan of pi over 4. Again, from Sohcahtoa, tan is equal to the opposite over the adjacent. Now we need to look at our other triangle here, the one involving pi over 4 angles. You can use whichever pi over 4 you like. In this case, let's choose the bottom one. Opposite side has length 1, adjacent side has length 1. So tan of pi over 4 is 1. Now we can take a look at our reciprocal trig functions. The cosecant function is the reciprocal of the sine function. So cosecant of any angle is the same thing as 1 over sine of that angle. The secant function is the reciprocal of the cos function. So secant of x, or secant of any angle, is 1 over cos of that angle. And then finally, cotangent of x, that's going to be 1 over tan of x. In other words, the cotangent function is the reciprocal of the tan function. So let's calculate a few more values here. Let's start with, say, cosecant of pi over 6. Well, there's a couple things we might want to do first. We could maybe draw our special triangle. Let's do it up here. So our 1 root 3, 2 triangle, and the angles here, pi over 3 and pi over 6. Right? The other thing we might want to remind ourselves is Sohcahtoa. It does help to have this written down in front of us when we do this calculation. So first thing I'd think about is cosecant is the reciprocal of sine. So if we look at Sohcahtoa, sine is the opposite of over the hypotenuse. If we instead take the reciprocal, we're getting the hypotenuse over the opposite. Okay, and then we can circle our angle pi over 6 here. We're going to work with respect to this angle. The hypotenuse of the triangle is 2. The opposite side is 1. So cosecant of pi over 6 is 2. Okay, if we want secant of pi over 6, we have to remember that secant is the reciprocal of the cosine function. So if cos of an angle is adjacent over hypotenuse, then secant of that angle is going to be hypotenuse over adjacent. And again, if we look back at our triangle here with respect to the angle pi over 6, the hypotenuse of the triangle is still 2. The adjacent side is root 3. Now, sometimes in dealing with these trig functions, we do get square roots in the denominator. So we would like to rationalize our answer here. Let's multiply top and bottom by root 3. On top, we'll have a 2 root 3, and in the denominator, if we multiply by another copy of root 3, we'll have a full 3 there. So 2 root 3 over 3 looks good as a final answer there. All right, let's try one more. Let's say we want cotangent of pi over 6. Well, we can go back to Sohcahtoa and say tan would be opposite over adjacent. We actually want the reciprocal of that, so adjacent over opposite. Still doing that with respect to this angle, pi over 6. So the adjacent side, root 3, the opposite side, 1. So just root 3 would be our answer there. Next thing that we'd like to work towards is some important trig identities. So to do that, let's remember that tan of any angle can always be written as sine of that angle divided by cos of that angle. So we can always write our tangent function in terms of the basic trig functions, sine and cosine. And because cotangent of x is the reciprocal of tan x, that means cotangent of x is just going to be cos x over sine x. Okay, so there's a couple of basic facts there. Now, when working with trig functions, there's a little bit of notation here that's important. Often we'll write things like sine squared x, and this is a little bit of shorthand. What it actually means is figure out the value of sine x and then square that value. So it's very important that we're interpreting this correctly. Sine squared x means the value of sine x squared. Similarly, if we write something like cos cubed x, that's exactly the same thing as saying cos x all cubed. So it's just simply a little bit of shorthand that we use so that we don't have to have big brackets going on everywhere. So with that, we can talk about one of our key trig identities, which is the fact that sine squared x plus cos squared x is equal to 1, and that is true for any angle x. So I'm just going to write for all x. Any real number x that you put into here, sine squared x plus cos squared x is going to equal 1.